So, part two of our little physics adventure today. When we last left our physics heroes, we were talking about interference, and we looked at interference in those sort of circular waves in a wave tank or a ripple pool. Then we talked about constructive and destructive. So the other way to look at that is that displacements that are in the same direction will produce constructive interference. If you've got displacements that are in the opposite direction, you get destructive. And you can have total constructive. So this is pretty close to total constructive. At every single point, if you put these two on a graph, the displacement is in the same direction. So at every single point, they're amplifying one another. Here we have what really is total destructive. So at every single point, they are opposing one another. And total destructive interference leaves you with no wave whatsoever. This is the principle behind noise canceling. I'm not sure how well it works, but the idea of like noise canceling headphones is that they produce a wave pattern which is supposed to cancel out other wave patterns. Like I said, I don't know that it works. That's really it. And we looked a little bit at how we can actually do this on a graph just by adding up the displacements to get a resultant wave. And they don't often they really don't usually end up giving you total constructive or total destructive. We usually end up with waves that aren't quite lined up that give us really funky stuff like that. Okay, so that's the basics there. There are some cautions with constructive interference. When we do this superposition idea, like adding up the displacements on a graph, this works within a reasonably small scale. Once you get into really, really large waves, you get into more chaos than we can account for. And so it's the whole thing where in most of physics we kind of ignore a lot of stuff and we go with the big idea. So in theory, you can do that sort of additive stuff to get a resultant wave. But once you get into larger displacements, you really can't. It doesn't work anymore. Okay, so destructive, and we talked a little bit about the fact that, as long as the displacements are in opposite directions, you end up with a smaller resultant. That's if they superimpose perfectly. And, looking at that graph, looking at the picture, we said very often they're out of phase a little bit, so you get complicated patterns. But in both cases, for constructive and destructive, it's just really the sum of the individual displacements. If they're equal and opposite, we get total destructive interference. We have no wave whatsoever. If we have a pulse wave where we have one wave traveling and one wave traveling and they meet, it's pretty easy math. When we get into something that has a repeated wave pattern like a sine wave or a periodic wave, it gets much more complicated, and pretty soon it all breaks down into a lot of chaos. So it's hard to really achieve perfect destructive interference this way. But we pretend, we can fake the math. It's more complicated than we are willing to do here. And I will give you a moment. I'll read it to you. What the heck? This is XKCD, one of my favorite comics, a web comic of math, romance, and sarcasm. I love these people. Clatter, 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 clatter. So I'd like you to all be the irritating person who's jiggling a leg. You've been that person. Can you feel the vibration in your desk next to you and in the desk next to you? Okay. Clutter, 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 clutter. Excuse me. You're jiggling your leg up and down, and it's traveling through the door, and it's making my desk resonate. Oh, I didn't even realize. I'll stop. Actually, could you just shift the frequency up by 15%? I think we can get resonance with Steve's desk instead. Here are the calculations. Let's coordinate it and try to spill his drink. This is what happens when you have an office full of geeks. So anyway, let's talk a little bit about reflection. So you noticed when you were doing your pulse waves out in the hall that the wave would start to kind of come back. And there are two different kinds of reflection. So we're actually going to go to the little wave simulator piece of software that we used before and look at that. So if you are interested in trying to observe different components of wave behavior, you can download String for free. It's a free app available for iPad. It may be available for Android also, I don't know. But that's one way to look at wave behavior. You saw what happens with reflection, and I wanted you to see that, not just talk about it. So if the end is free to move, the wave is reflected identically. If it's fixed, it's reflected in the inverse. Okay, great. What fun. Now, woohoo! That's the same thing. Inverted reflected pulse with a fixed boundary. This is the fun part. So these are standing waves. And this is what we did with the clothesline and the drill and the weird rigged up. Yeah, looks exactly like what we did here. So it's a wave pattern that doesn't move. Hence why they call it a standing wave. Standing, not moving. I know, it's crazy. It's really creative. Those physics people, they're nuts. All it is it's actually a pattern of repeated constructive and destructive interference. So you have a wave, and this is typically a wave that's being reflected back along whatever medium you're seeing, and the reflection interferes with the oncoming wave until you get, if you get it to just the right point, you get an area of maximum constructive interference, and you get an area of maximum destructive interference. So you have a point where the amplitude is great and a point where the amplitude is 0. Okay? It's just repeating patterns of constructive and destructive interference. You can actually observe standing waves not only on strings, not only on ropes. You can see this in water, and if you go down to Lusk Lock, how about this? I give you homework. Go to Lusk Lock. It's a beautiful spring day. Lusk Lock off Middle Beaver Road. Okay, well, go sometime this week. And when you park, get out of your car and go that way. Go upstream, whatever that is. And as you round the bend, there's a corner in the creek, and there's a big rock. And if you look at that rock and you stand there or you sit there, and you could sit there for hours and stare at that wave, there is a standing wave there. Never seems to move. It's cool. It's weird. And it's you can see standing waves in moving water sometimes. But we usually in physics just look at them on strings. So there are names for the portions of a standing wave. This looks like a little bow tie or something. I don't know what it looks like, but perhaps art. The points where there is destructive interference are the nodes. So the points where it pinches down and there's essentially 0 amplitude, those are the nodes. The antinodes are the areas of constructive interference. Okay? So antinodes are the big fat parts. They're the parts where you actually have constructive interference and you have maximum amplitude. Okay, when we're looking at one of these systems, so we have a piece of string, and I'll draw something vibrating at its first harmonic. So that string is vibrating. I mean, you saw with that rope that I had on the drill. The whole piece of string was moving. Now, there's one little point in the middle, that node, where there really is no amplitude. There really is 0 amplitude, and that point isn't vibrating. Every single piece on that string has the same frequency, which seems counterintuitive because they have different amplitudes. Clearly, if we were to, oh, that doesn't blow it up for you. Let's say, clearly, if we were to look at a point here on the string versus a point here on the string. So this point is not going up as high. Let me see if I can magnify that. There. Okay. So looking at this point on the string versus this point on the string. This one vibrates much farther away from equilibrium. And remember, this is a mechanical transverse wave, so it's each individual point is just going up and down and up and down and up and down. Each point is not doing this. They're just going up and down and up and down and up and down. This point doesn't go as far. It doesn't have the same amplitude, but it has the same frequency. Okay? That point is vibrating with the same frequency. So it takes the same, it will complete the same number of cycles of motion per second as this point. Okay? Okay. You can have multiple different standing waves on a string, and I tried to create a couple different ones on the drill and clothesline. I think I got 2 and 3. Did I manage a 3 humper? Yeah. So essentially 3 nodes, 1, 2, 3 nodes, and I got a 4-node standing wave. So a 3 anti-node standing wave, a 3 humper. Only some frequencies will actually create a standing wave. Did you notice that when I was playing around with the drill and the rope, sometimes it just kind of went floppy and sort of spastic and it wasn't really doing anything? The wrong frequency, well, in that system it's a combination of frequency and tension. But it was just not one of the frequencies which would create a standing wave. Essentially I was adjusting the length of the string by moving the drill. It's not a perfect replica, but it works. And if we were doing the music chapter, I'll kind of preview it here since we're not going to get to do it. Each of these wavelengths and frequencies would be a musical note if we were looking at this on string. And there's a slightly different series in like closed pipes. So these... Each standing wave is a note. Now for a pipe or a string of a given length, the fundamental frequency is the one that you usually hear, but then you'll hear a combination of the other, these are called harmonics. So in any given instrument, the tone of every note is a combination of the fundamental frequency, which is the first harmonic, and what you hear is then a blend of the undertones and overtones are the upper harmonics. So how many musicians do I have in here? 1, 2, 3, 4. 4? Okay, we've got some singers. Okay. What you're doing when you... How many of you have seen a guitar? Okay, good. How many of you have seen somebody play a guitar? Excellent. And they put their fingers up on the neck. Yes, on the fretboard is what I was thinking, but yes. They put their fingers on the neck. They push down on the strings. When they push down on the strings, guess what they're doing? Shortening the strings. And hence, changing the length of the string changes the fundamental frequency, so you get a different note out of the same string. Okay? And changing the tension also changes its ability to vibrate at the frequency that you want. So, okay. We get standing waves. So let's actually not do this slide. Let's talk this through real quickly. So if I have a string of that length, and I'm going to copy this string repeatedly, because this makes no sense, I think. If you try to just talk about it academically, you have to draw it. So I have, some, let's say, guitar string. It could be a piano string. All a piano is a bunch of guitar strings hidden in a box. Basically, it's a harp with a box around it, and you strike it mechanically rather than plucking it. You knew that, right? Good. Okay, so I have this here string. And I can, let's say that this is a 1 meter piece of string. Okay, or guitar chord, or harp chord, whatever. I can get it into a standing wave that looks like that. That would be the fundamental frequency. That's the first harmonic that's possible. So, what is the wavelength for that wave? Be careful. Think about what a wavelength is. 2 meters, because you have to go from equilibrium back through equilibrium and back. So for that string, the wavelength of the very first harmonic, the wavelength being what symbol? Lambda. Lambda is 2 meters. Yeah, upside down Y, which is broom, whatever you want to call it. Okay. So lambda of the fundamental, lambda 1, is 2 meters. Well, I could also get a standing wave going that looks like that. What would lambda be for that? There, lambda is 1 meter. Okay. Well, I could get a standing wave. This is the hardest one for me to draw always. Okay, we'll finish this conversation up tomorrow. So there's our third harmonic, and we'll pick up with that.